This is the second part of the enzymatic catalysis, where we're going to focus on the mechanisms as well as types of catalyses. To show the catalytic mechanisms from the reactants to the products, all the molecules that are involved are laid out, connected by the straight arrows, which indicates each step of the reaction. And on each step of the reaction, the curved arrows are used to show the flow of the electrons or the electron pair. So in this case, the electron was here, but it flows to here to make the electron pair. So this is an example of amine interacting with have the reaction with the aldehyde or the ketone to form the imine, which is a shift-based structure here. And this shift base is really important because it's used to form the many important catalyses. Largely, there are 5 different types of catalysis: acid-base catalysis, covalent catalysis, metal ion catalysis or electrostatic catalysis, proximity and orientation effect, and finally preferential binding of transition state. And we're going to go over each type of catalysis, and we'll study much more in depth about their mechanisms. And actual enzymatic reaction mechanisms often combine more than one type. So keep in mind that some enzymes will fall into multiple categories. And the first one is acid-base catalysis, which accelerates the reaction rate via partial proton donation by a catalyst in general acid catalysis, or partial proton abstraction in the general base catalysis. Now let's talk more about these general acid and general base catalysis, as well as their differences in their mechanisms, by looking at this keto-ethyl isomerization. And you should be familiar with this keto or enol forms, which were covered in previous lectures. And when they change their forms, they go through the transition state where this hydrogen atom is partially positively charged by giving up the electron to the carbon atom, where it now has the excess electron, so we'll have electron negativity, as you can see here. And by the electrostatic attraction, this positively charged hydrogen atom will make the covalent bond with the oxygen atom here, which is negatively charged, to get to make the enol form. In case of having the general acid catalysis, this general acid, which is shown here as HA, will provide the proton partially. A proton works as a partial proton donation, as it is written here. And what the proton does is getting rid of the electron from the keto form. So it easily makes the electron negativity here, which will boost this transition state. And as a result, the hydrogen atom gets out from this keto form here, and then it forms the enol form. And the rest of this salt of the general acid will be restored as the acid by adding the water molecule. And general base catalysis will be a different story, still using the keto form here, but providing the general base here, which will attack the hydrogen atom here. Of course, it works as a partial proton abstraction, so it get rid of this proton, the hydrogen atom, or actually gives more electrons there a little bit. So it will have the positive charge again, and will help the electronegativity formation of the other region of this keto form, will induce this transition state. And by adding the hydrogen atom, it will form the enol form, and this H with the B plus can be divided to the general base again, and can be reused to form this transition state. And effects of pH on the enzyme activity are often due to altering the protonation states of amino acids such as aspartic acid, glutamic acid, cysteine, tyrosine, histidine, lysine, and arginine. And they participate in acid-base catalysis by having the peak activity or the rate at around the pH 7. RNase A, which breaks down the RNA molecule, is a classical example of acid-base catalysis. How it works is that the two residues in the active site, the histidine 12 and histidine 119, are critical for this such catalysis. So it works in the two steps basically. On the first step, the histidine 12 abstracts the proton from this hydroxyl group on the 2' of the RNA sugar, promoting the nucleophilic attack of this hydroxyl group to the phosphorus. And histidine 119 acts as a general acid in this case, which is from this hydrogen atom, and it protonates the leaving group, which makes the bond breakage. So this leaving group leaves from the active site, and after that water molecule comes in, but this one, which was induced by histidine 12, would form the intermediate state where it has the 2', 3' cyclic nucleotide. And the second step would be that this 2', 3' cyclic intermediate is broken by this water molecule and the histidine 119, which act as a base in this case that attacks the this phosphorus. And in this case, the histidine 12 now, which has the hydrogen atom added to that, works as the acid, which donates its proton to make the hydroxyl group on the 2' of the RNA sugar here, and then the rest of the molecule will leave the active site of the enzyme, the RNase A, to complete the process. And the second type of catalysis is covalent catalysis, which accelerates the rate through the transient formation of covalent enzyme substrate intermediates. And usually a nucleophilic group, which is electron rich, so it loves the electron division centers, attack an electrophilic group, which is electron deficient, so it loves the electrons, and form the covalent bond with it to form the this kind of shift base here again, imine structure in this example. An example of a covalent catalysis is a chemical catalysis of decarboxylation of acetoacetate by primary amine as a catalyst via shift base. So acetoacetate becomes to acetone through this intermediate called enolate by have the carbon dioxide as a leaving group and addition of the hydrogen cation. But this can be accelerated by adding this primary amine as a catalyst. In this case, it comprises these mainly 3 steps to get to this catalysis. And first step will be the nucleophilic attack by the catalyst, where it forms the covalent bond with the acetoacetate. In this case, this group that is neurally generated is going to be electron division, so naturally we'll extract the electron from the reaction center on the carboxylate group of the acetoacetate. And in this case, it already forms the shift base, and so it's a critical step for the catalysis. So electron moves to towards this newly formed group, which will induce the elimination of the carbon dioxide. And now the excess of electron will push down the electron to the down to the rest of this intermediate stage. With the addition of hydrogen cation, it will go back to this form where it was originally attached. So it will induce the elimination of catalyst, which is basically the reversal of this step 1. And then by addition of the hydroxide, this will become the acetone in much faster way. Nucleophilicity, which is a property to love a proton, is related to basicity of a given group, and basicity is the property to prone to accept proton. So they are related, but they are different because nucleophiles, which have nucleophilicity, covalently bond to electron deficient centers. However, bases are prone to abstract protons from other molecules. Here are some examples of nucleophiles and electrophiles. Some examples include the molecules that contain hydroxyl group, sulfhydryl group, amino group, as well as imidazole. And examples for the electrophiles would be protons, metal ions, carbonyl-carbon, as well as cationic imine, group carbon. And the good covalent catalyst must make a good leaving group too. So it depends on the reversibility of the bond formed. So since this is a covalent catalysis, this catalyst will form the covalent bond with the intermediate. But the problem is that that covalent bond has to be broken to become the final product, and also this catalyst should leave from that intermediate. So the reversibility is the key for making such a breakage, and that property is correlated with the polarizability of the intermediate, which reflects the how much mobile the electrons are within that intermediate molecule. And the third type of catalysis is metal ion catalysis, which is widespread. And almost 1/3 of all enzymes require metal ion for catalysis. There are two classes of the metal ion catalysis depending on the strength of interaction. The first one is metalloenzymes, which have tight bonding to the metal ion, and usually it uses a transition metals such as iron, divalent or trivalent ions, and copper, zinc, manganese, and cobalt ions, and so on. And the other class is the metal-activated enzymes, which have loose binding of the metal from the solution. And typically, the alkaline or the alkaline earth metals are involved in such metal ion catalysis, including sodium, potassium, magnesium, and calcium ions. And this metal ion catalysis acts in three distinct ways. It can bind to substrates and orient them properly for the reaction, and it can also mediate the redox reaction, oxidation reduction reaction, where the protonation and deprotonation is involved, by transiently changing their redox state, oxidation reduction state. And we're going to discuss much more in depth about these redox reactions in the coming lectures. And also, the metal ion catalysis can stabilize and shield the negative charges to achieve the catalysis. An example of a metal ion catalysis is the phosphate group transfer from the ATP. And in here, the real substrate for the kinase, which breaks down the ATP, is not simply just the ATP, but magnesium ATP, and magnesium ion shows the negative charges of these phosphate groups that will otherwise repel the incoming nucleophiles, in which case it's right here, that often have the negative charges. So it stabilizes these negative charges to induce this breakage of the phosphodiester bond. And an example of the metal ion catalyst is carbonic anhydrase, which catalyzes this reaction, where the reactants are carbon dioxide and water molecule, and the products are bicarbonate and hydrogen cation. And here especially the zinc ion is used, which is coordinated by 3 imidazoles of the 3 histidines that surrounds in this zinc ion, as well as water molecule in the active site. So upon the opening of this active site, zinc ion helps to get the electronegativity of this oxygen atom, which attacks the carbon atom on the carbon dioxide, and that leads to the covalent bond between this oxygen and the carbon atoms, and to form the bicarbonate. And with the addition of water molecules, now this enzyme can be reverted back to its original form, and with the release of a hydrogen cation, this bicarbonate can be generated. And the next type of catalysis is proximity and orientation effects. And in this effect, binding of substrate to the enzyme forces the substrate molecules orient in a certain way so that their active groups face each other to poise and to react. So this is an example of that geometry orientation for to boost the reaction. So let's say that this is a substrate and this is the enzyme, or you can actually think that these are two reactants as a substrate. But either way, they are two different molecules are oriented in a proper way where the functional group has to face the other molecule from the one molecule, so they can be easily form this intermediate state from the sp3 hybridization to the sp2p hybridization, and then now this transfer of the functional group will be much easier, and then transfer to the new one to finish this catalysis. And it's called a backside attack. In addition, it also make the rotational or translational motions or the vibration minimum. So the enzyme can just hold this substrate from moving around for the further process with the other reactants or the reaction of the substrate itself. And the enzyme also can get rid of this solvation shell from the substrate to boost the interaction with the other reactants or the process itself too. And also enzyme and the substrate uses electrostatic interactions or the attractions for better interaction between these substrate and enzyme or the other reactants too. And that the proximity and orientation effects comes at the expense of loss of entropy, because now substrates are not really diffused here and there, but it's actually have to be held within this enzyme. So the internal energy level should be raised there, but that energy is recovered from binding energy between the enzyme and the substrate. Transition state analogs are really critical molecules that resemble the structure of actual substrate of an enzymes and that you want to study or that you want to control. And this is critical for studying the enzyme's activity as well as mechanisms. And many enzyme inhibitors are in fact structural mimics of a transition state intermediate. And sometimes it is possible to synthesize a stable molecule, and you can also find it in the nature too, a stable molecule that happens to resemble the transition state of the reaction, which is typically unstable. And this is an example of the reaction that is catalyzed by the proline racemase, where it changes the L-proline to D-proline and vice versa too. And it has the this intermediate state, and this racemase has the transition state analogs, and that was discovered that basically mimics the structure of this intermediate substance. And these transition state analogs, or the TSA, as we expect, bind to the enzyme's active site really tightly, because enzymes are optimized for binding the intermediate substrate. And so they can act as a potent inhibitors of the enzyme. And this transition state analogs also can help confirm the structure of the natural transition state. And transition state analogs are also useful because they can be sometimes used for co-crystallization of the enzymes in order to obtain the information about the catalytic mechanism of the enzyme. So in many cases, if enzyme and the actual substrate is used, it will be quickly change it to the intermediate state, and then will produce the product or go back to the substrate. So it'll be really hard to catch that moment where the intermediate state of the substrate is achieved, and how enzyme actually works on that. So by using this transition state analogs, you can just put the enzyme in that transition state for a long time, as it's not gonna further process to the making the product or back to the reactants. So you can easily just study about the enzyme structures, active sites, as well as the mechanisms how they bind to the this intermediate. Now let's consider the entropic and enthalpic factors in catalysis, which can explain how enzymes can reduce the activation energy of the reaction. So let's bring back the thermodynamics here, and I hope you're already familiar with this equation where you can get the Gibbs free energy. And delta G naught double dagger will be the free energy of the activation, and that can be also gotten by the delta H naught double dagger, which is enthalpy, minus T delta S naught double dagger, where T is for temperature and S is for entropy. And in the catalyzed reaction, the overall activation energy delta G naught double dagger is going to be lowered during the catalysis, and that means delta H naught double dagger, the enthalpy, should be decreased dramatically, or the entropy can be increased. But when you actually look at the entropy and think about that, the substrate and enzyme will make a complex, the ES complex, which will make the entropy lowered. So you're gonna have the smaller value here, which can actually affect the delta G to be increased. So that's not good for the catalysis, but this increase of entropy is offset by the large reduction of this enthalpy decrease. So in order for the substrate molecules to reach the transition state, which is required for the reaction to occur, they often undergoes the structural changes that require a lot of energy, and that leads to some like straining or the distortion of that the enzyme or the substrate. But enzymes can bypass this energy requirement by binding strongly to the substrate and changing their shape, and thereby forcing them into the intermediate state that resembles the transition state, but it is with the lower free energy. Now let's shift the gear and study the kinetics of the enzymes, which is one of other sisters for studying enzymes. The other one was the structural biology that we talked about so far. And kinetics can also help us learn a lot of things about enzymes, like the enzyme properties and binding of substrate to enzymes, and also we can get the idea and the measurements for how strong that the interaction is, and the stoichiometry, and what forces are contributing to those bindings, and so on. And also we can learn how enzymes react to activators and inhibitors over time with the dynamics. And also we can learn what steps take place along the reaction pathways for the enzymatic reaction. Before we get to enzyme kinetics, let's have a review of chemical kinetics which have the same logical basis. Let's consider an elementary reaction of a conversion from A to P, and it could be either direct reaction where A changes to P, or a sequence of elementary steps from A to I1 to I2 to P, where I1 and I2 are intermediates. If it's the case of this sequential reaction, then overall reaction cannot be faster than its slowest step, which can be either from A to I1, I1 to I2, or I2 to P. And this particular step is called as rate limiting or rate determining step. An important goal in analyzing a pathway is a precise definition of each step, which leads to understanding of the catalytic mechanism. So for the reaction A to P, the rate or velocity is described by the V, the velocity or rate, equals minus differential of the concentration of A, or the differential of concentration P, and that is by change in concentration of the reacting species over the unit time. Rate law describes a mathematical relationship of reaction rate or the velocity to the concentration of the reactant. So for the reaction A becomes the P, the V, the velocity or the rate, will be the minus differential of the concentration of A, which equals the product of K and the concentration A, where K is a rate constant. And this particular reaction was a unimolecular reaction where the one molecule was used as a reactant. If the reaction requires a collision of the two molecules, then the reaction would be A plus B as reactants, would be the C plus D as products. And then the rate or the velocity V would be the product of K and the concentration of A and B. And this equation, the V equals K, A and B concentration, is a second order rate equation. And that means this reaction was a bimolecular reaction where two molecules work together as a reactants for this particular reaction. And here K is a second order rate constant. And in general form, if you make it into the more than two molecules collision for the reaction, then that will be A as a coefficient, basically the ratio or the concentration of this A molecule. So little a, big A, plus BB plus CC to the ZZ, which makes the product P. And that is described by the rate equation velocity or the rate V equals the product of K and basically A to Z with their exponents equal to the coefficient for this reaction. So basically this would be, instead of the second order rate for this two molecules reaction, the bimolecular reaction, this would be 26th order rate equation where the A to Z, all the molecules were involved for the reaction. Thus coefficient on here becomes the exponents in rate equation. So the reaction order is given by its exponent. So for the rate or the velocity as the K and the A concentration and B to the 0th, that would be the first order reaction in A, but the 0th order in B because the exponent is 0, which means that this reaction is independent of concentration of B, and the first it will be the first order reaction overall. And the reaction described by the V equals the product of K and A B concentration will be the first order with respect to A and B individually, and the second order overall. And this order corresponds to molecularity of the reaction, which is the same as the number of total molecules that must simultaneously collide for such reaction. So in case of this A to P reaction, that will be first order because just one molecule was involved for the reaction, which is a unimolecular reaction, as opposed to this one, A plus B, becomes the P plus Q would be a second order reaction where it is a bimolecular reaction, and so on. And as a chemical reactions are usually 0th, 1st, 2nd, and rarely 3rd order reactions where 3 molecules are involved for the reaction, and the tetramolecular reactions are not known to date. Most of the formalisms that we discussed so far for the chemical kinetics is applicable to enzyme catalyzed reactions, but there's more to consider. And as we did so far, we'll still call the enzyme E, substrate as S, and product P, and substrate or substrates are the reactants that enzymes act upon. And this enzyme catalyzed reaction has a special and interesting property called substrate saturation effect. And that is, for the reaction S to P, substrate to product, the plot of the initial reaction rate as a function of substrate concentration against the velocity of the reaction for chemical reaction is linear. And that means that the rate or velocity V which is a product of K and the concentration of S, will make the straight line here with a slope of K. But for this enzyme catalyzed reaction, when you especially look at the extended window of the substrate concentration for the higher concentration for substrates still, the plot is hyperbolic. So you're gonna see that this velocity gets slower and slower, so the slope gets more like a flattened, and then we'll see a plateau at the end where the velocity is at the maximum speed. And note that we'll only deal with this initial reaction rate where the velocity makes in this straight line, which allows us to ignore backward reactions where products go back to substrate, which makes this concept or the calculation complicated. Now let's consider enzyme catalyzed reaction in more detail. So when we go back to this plot where it shows the relationship between the velocity or the rate of the reaction and substrate concentration, in the beginning right here where the concentration of substrate is low, the rate or the velocity is proportional to the concentration of substrate, as in the chemical reaction you have the linear relationship as one would expect for the first order reaction. But as concentration of substrate increases, the V or the velocity levels off at certain maximum level as called Vmax, which is the maximum velocity, and now the reaction rate becomes independent of this substrate concentration as it gets to the plateau for the velocity or the rate. So that's going to be the 0th order for the S. And such curve is called a substrate saturation curve. And enzyme forms a complex with S, the substrate, during the reaction, and at the high substrate concentration, every molecule of the enzyme will be bounded by substrate to form this ES complex, and that is to say that as soon as P is formed, that the product is formed, another molecule of S jumps on to the enzyme, or as soon as S dissociates from the enzyme in case of unproductive binding, another S will jump on the enzyme to make this ES complex. Thus, the substrate saturation effect suggested to entomologists that there exists a direct interaction of E with S because there is an equilibrium that is formed between this E and S to form the ES complex, and that is contributed to this plateau and get to the Vmax. So that was a cornerstone of the enzyme kinetics, and from there the entomologists built up their models to explain how enzymes work for processing the substrates. Michaelis and Manton proposed a general theory of the enzyme action in 1913, which became the foundation of modern enzyme kinetics, and that was built upon the ES complex concepts. So Michaelis and Menten introduced the assumption for the simplification, and the simplification is basically that they assumed that there is an equilibrium between binding the E and S and dissociation of ES complex back into E and S. And that is that that they assumed that this K2, the constant for the ES becomes the enzyme, and the product is much smaller than K minus 1, where the ES complex goes back to E and S. Therefore, since this K2 is much smaller, we can ignore the K2, and therefore this simplifying assumption states that the conversion of ES complex into E plus P is much slower than dissociation of this ES complex into E and S. Like we said, K2 is much smaller, so it will generate this E and P in a much slower or the smaller rate. So again, this can be simply ignored in this Michaelis-Menten theory. But this is not always true, but can be applied in many and several cases of how the enzymes that is working for the reaction. And if the reaction of a formation of ES complex is the same as the rate of a breakup of the ES complex, then this rate, which is called as Ks, the substrate constant, will be the concentration of E and S divided by the concentration of ES complex, which is the same as the ratio of the rates, or ratio of the constants, K minus 1, which is for the ES to E plus S, divided by the K1, which is for E plus S to ES, and that is the same as the equilibrium dissociation constant of ES complex, so it can be written as KD too. Briggs and Haldane added another idea to Michaelis-Menten theory in 1925. They've decided that this Michaelis-Menten simplification is too restrictive, so they suggested that ES complex during the reaction is at steady state. So this will have the sort of a constant concentration during the reaction. So again, the concentration of the ES complex is constant value during the reaction, and that tells that this ES forms as rapidly as it is consumed by the sum of two routes here. The first one is basically from the ES to the E plus S by ES dissociation, and the other route will be in this direction, where ES dissipates into E plus P until S, the substrate, is depleted. And this is called the steady state assumption. So it still makes this ES concentration constant. And is this assumption true? And that is generally yes. And the ES steady state here, the constant concentration value of the ES complex, can be directly demonstrated and measured in special apparatus called the stopped flow apparatus. And from those measurements, this assumption was justified by measuring that, and it's a success in predicting the experimental results for many enzymes. So from the Michaelis-Menten theory as well as Briggs-Haldane assumptions, we can have this sort of the overview of how the enzyme works for the reaction, for its catalysis. So of course the substrate concentration will at the maximum level of right at the beginning of this reaction, and will go down like that, as opposed to the concentration of the product will start from almost 0 and then will go up steadily, and there's an anti-correlation between the substrate and the products. And when you look at the enzyme, quickly it will form the ES complex, and we'll get to the maximum point in the plateau where it has the steady state. And they're gonna be the differential of the ES complex concentration is almost zero. So again, this concentration of ES is constant at this steady state, and that's where the reaction is at Vmax, the maximum velocity or the rate. So, but the total concentration of enzyme will be the same as enzyme that is unbound to the substrate, as well as ES complex all the time. So when you look at the focus on this smaller region, the initial stage of the reaction, they're gonna be the total enzyme that is unbound, and then quickly the substrate will be bound to the ES, which makes just the unbound enzyme concentration goes down, as opposed to ES complex go up rapidly. So the slope is really steep, and then it goes flatten and flatten to meet this plateau again to get a steady state, and the product will be increased over time with the higher speed, and then it'll be also with the constant speed, because all the enzymes are now utilized there.